So I'm going to discuss the angular equation of motion for non-spinning rockets. So right now, in the next videos, I'm only going to talk about non-spinning rockets. Okay. When we have spinning rockets, things complicate a bit. There's a thing called spin stabilization, which is actually the reason why, for example, non-statically stable, let's say, vehicles can stabilize, like bullets, for example. As you recall before, the aerodynamic center for something like this is going to be somewhere near the front, and if the center of gravity is here, well, this is unstable. The bullet is statically unstable. We call it statically unstable one. Yeah, if this has a small angle of attack, well, the forces that appear are gonna try to destabilize it even more. So that is statically unstable or statically stable. But if this is spinning at a really high frequency, well, it is still statically unstable, but things get trickier because it's not gonna destabilize that fast. Let's say we might look into spinning rockets in the future, but for now I'm only going to treat non-spinning rockets. Okay, so for non-spinning rockets, the angular equation of motion is simply the sum of moments equals the longitudinal moment of inertia. So first and last time I'm going to put the subscript L for the moment of inertia. So when I talk about the moment of inertia, it's just, obviously the longitudinal moments of inertia of the rocket. Okay. Delete this. Times the angular acceleration. 2 dots means twice derivative in time. Okay. And the only moment here we have is due to the normal force. So we have n times the position of the aerodynamic center of gravity. And as we saw before, this we can let's see. We can see the moment as well as the. I don't know why this bit. We can see this as the sum of the moments due to each of the parts. So the normal force due to the fins. Yeah. And you get the idea. Alright. And now we're going to introduce the concept of the corrective moment coefficient, which is the normal force divided by the dynamic pressure times a reference area A. And unless we're talking about drag, I'm going to use the letter A for the reference area, and the reference area is always going to be the cross-section of the rocket at its diameter. So D is the diameter of the rocket, and A is the cross-section of our rocket, and this is just the dynamic pressure, so it's half of the air density times the velocity of the wind, of the incident wind. Okay. Actually, I shouldn't put maybe the subscript infinity, because as I told you before, this is, you could see this as only the wind, not the incident air velocity. So I might drop this term. Before we discussed that the incident air velocity is the wind plus the velocity at which the rocket was moving, and we're going to see plus, it's actually plus another velocity we're going to see further on. So, well, don't worry about this. Let's just leave it. It's a dynamic pressure of the incident wind. Okay, so we're going to use the normal force coefficient from now on, because you can find data of the normal force coefficient for fins and for everything. You're not going to find, obviously, data about the normal force. You're going to find it dimensionless. So then you can, from going to a dimensionless factor as the normal force coefficient here is just multiplying by q and times a. So we're going to find these guys in the literature, okay, and the position of the aerodynamic center. So finally we will arrive at, it's not a final form, we're going to further develop that, but right now we're at here. By the way, I'm going to drop now. It's a good time to say, for the rest of the analytical analysis on the, oops, sorry for that. Let me get back if I can. Okay. All right. Maybe I have to introduce a bit what I'm going to do about from now on. Right now, I'm going to do an analytical analysis on the stability of a non-spinning rocket. Okay. So, let's see. Up to now, I haven't done any simplification. Well, only the fact that the rocket is not spinning, which is already okay. It is already a simplification, because this is a simplified equation of motion. When the rocket spins slightly, this is not valid. And rockets do spin, even though we don't give an angle to the fins. So that's a thing you have to worry about, actually, that rockets are going to spin even though you don't want them to. So from now on, I'm going to do my goal here. I'm going to do it video by video, step by step. My goal here is going to be to do an analytical analysis of stability. So what I'm going to do is, for stability, I'm going to drop the term related to the normal force coefficient due to the boat tail and other conical transitions. This is not really relevant, to stability. I mean, it compared to the rest of the forces, of course, order of magnitude, it's going to be really relevant in drag, but in stability, we're going to drop that term. Relevant in stability. So right now, I'm going to move down. So the equation we have right now, if we drop the term of the conical transitions, is the following. We have the normal force coefficient of the fins, then we have the term of the body, oops, CG, and on the other side we're going to have the longitudinal moment of inertia divided by this. Okay, so we have this equation right now. This is the equation that if we can solve for alpha, which is the angle of attack, but alpha is buried in here. We have here the acceleration at which a rocket is oscillating. Okay, so the rocket is here. This is alpha. So if it destabilizes it, if something destabilizes the rocket, it's going to be moving from side to side. Okay, it's going to have an angular displacement, which is the angle of attack. It's going to have a speed at which this displacement, this perturbation, or this is moving. So this is the angular velocity and the acceleration. So to go from one to another, we have to integrate. But what I want you to see is that alpha alpha is buried inside this equation. So if we're gonna look further into this equation, and ultimately our goal is to see, well, how this rocket is gonna oscillate and move when it finds perturbation. So let's move on.